Hello, Sky. Thanks for joining me. And I'm looking forward to discussing gravity with you today.
Mm. Hello, Rupert Sheldrake. It's a pleasure to meet you.
Hmm.
Mhm.
Good. Well, the reason I'm so interested in talking to you is because I've for a long time been interested in the way that the fundamental constants, so-called constants, seem to vary. And I first discussed that in my book, Seven Experiments That Could Change the World, in 1994. In a chapter called The Variability of the Fundamental Constants. And they went on varying. And so I discussed it again in my book, The Science Delusion. This is the new edition,
Yeah, which I have here. Yeah. Mhm.
2020. You've got the original edition, and I've got here, this
Mhm.
is the new edition.
It's a great
And
book.
and all the constants seem to vary, but the one that varies most is the gravitational constant. And when I found that the constants of physics varied, I was rather shocked because, like a lot of people, I assumed that physics
Yeah.
exactly. We'll come to that in a moment, but I was very shocked because um, a lot of people naively assume that physics is completely certain facts and the constants are all fully known and that kind of thing. And when you look at them in a handbook of physical constants, they're often defined to multiple places of decimals, implying an incredible accuracy. But when I actually looked at the constants, I found the gravitational constant of all the constants fluctuates the most. And in some cases, discrepancies of up to 1%, or more than 1%. And when I asked physicists about this, most of them just said, oh, well, it's just measurement errors. And they weren't very good at explaining why, when people are claiming enough accuracy to give three or four places of decimals, you could get such huge errors way beyond the claimed accuracy of the results. And so I came to the conclusion there must be something going on with the big gravitational constant, big G, the Newton's gravitational constant, that there must be a reason for these fluctuations. Either they actually fluctuate, a bit like stock market prices fluctuate, um, or there might be a systematic reason. For example, as the Earth goes through clouds of supposed dark matter, which is, physicists imagine there's all this dark matter, it might be in clouds, it might affect the measurements. There might be reasons for it. But I couldn't find any physicist to discuss this with who could see a reason or was even interested in the question. And then when I came across your work, I found that you were actually more than interested in the question. You'd actually been investigating this variation in the constants. You'd found that there was a systematic reason underlying these variations. And what's more, and what impressed me, was that you don't just talk about it. I mean, a lot of physicists never get beyond their desk or their computer or their whiteboard. You've, like any proper physicist, got sort of equations in the background. But
Yes. It's about the perihelion precession of Mercury and the Kepler ratios of the planets. Yes.
so, but when I found you'd actually been doing measurements, and moreover, doing them in conditions that you'd had to improvise in garages and things or workshops and so on.
Well, I measured the gravitational constant of water in a factory, in a family factory, but it was a very big factory and very good. But then later I went on to just look at all the measurements of the gravitational constant that exists that have been done and look at what materials were used, because according to my theory, it depends on the material.
Exactly. Well, that's it. You see, now, what I'd like to ask you now is to explain to everyone, and me especially, because I don't follow all your work very clearly. I don't know maths enough to follow all the equations and so on. But what I like about your work is that it's very empirical as well as being theoretical. And you're
Yeah.
obviously a really independent thinker. And let me say
Yeah.
one more thing before we get on to your actual explanations or hypotheses
Mhm.
about gravity. I get emails from physicists, or amateur physicists, it used to be like one or two a month. And now, with the advent of AI, it's become almost one a day. You know, people who've solved the mysteries of the universe, solved the hard problem of consciousness, linked it all to quantum theory, the Higgs field, dark matter, and dark energy, and they've got the complete explanation of everything. So theories of everything are now pouring into the inboxes.
Well,
Any scientist who's at all publicly known. And what distinguishes you from the many things that I've seen by physicists is, first of all, you really do seem to know what you're talking about. And secondly, you've been working on this for years. It's not just some AI printout. And thirdly, you've done the hard work of actually collecting empirical data and doing experiments yourself, which involves a lot of effort. So
yeah.
for all those reasons, I'm really pleased to have a chance to ask you. And now, what I'd like to ask you first really is, how do you account for these apparent changes in gravitational constant in these measurements, the apparent variations? Because you do have what seems to me a fairly plausible theory.
Thank you. When Newton came up with his theory of gravity, he had to make gravity dependent on something that increases with the size, with like gravity of a rock is you cannot feel it, but of the Earth and the Moon you can feel it. And the only thing you could think of was mass, because that was known at the time. He didn't know about atoms, otherwise he could have gone for particle count. And so in my theory, gravity depends on the number of particles, more specifically on the number of protons and neutrons. And the layman may now think, wait a moment, isn't this exactly the same? More particles, more mass, right? But since Einstein, we know that mass is a form of energy. And so there are contributions to the mass of an object that are negative. So iron, for example, has the most negative energy. It's binding energy. Nuclear binding energy is negative, and it reduces the mass, but it doesn't reduce the number of particles. And if gravity really does not depend on mass, but on the number of particles, then you have more particles per mass unit. Because mass is reduced, but not particles not. So you have more gravity. So that means iron has the most gravity of all the elements. And
You mean
that's also
per
supported
unit mass,
per unit
gravity
mass.
per
Yeah.
unit mass. I see. And can you just explain one more thing? When you said the gives it negative mass, reduces the mass, are you talking about the strong nuclear force?
The strong nuclear force, this has energy associated with them and binding energy, and this is negative, and it reduces the mass. And this does not only apply to the strong force. Earth also has negative energy, and if Earth is dense like it is now, it actually has less mass. If you could blow Earth up like a balloon, it would would regain some of the lost mass. So it has negative mass. So now it has 10 to the power 15 kilogram negative mass. And
Why?
it's similar with the atomic core. It's dense, and so it has negative binding energy.
So why does the Earth have negative mass? It's not obvious to me why it should have.
That's binding energy. It's because of the potential to do work, potential energy and kinetic energy. And so you have that for all the forces. And that's maximized here. This is iron. All of these elements are iron. And here's water. So here you have high gravitational constants.
I see. Could you show that more, maybe
Yeah.
on screen share, and then we'd be able to see it better?
Yes. Yes, one moment. Okay, so here you see it more clearly. And you
Yes.
see the different values by different people. And so this is encompassing all the measurements of the last 50 years, 55 years. But in the case of Hale, I included him, even though his measurements were done in 1930. That's the only high quality those are the only high quality measurements that are before 1970 or
And just
1969.
so what we got at the bottom axis here is these things, FAAU, etc.
Yeah,
These
these
are
are
the
the chemical
actual
compositions.
materials that were used for the measurements of gravity. And so,
Yeah, and there are always pairs of two because you have the source mass and the test mass.
and this is on the Cavendish balance, is it?
Yes.
Okay, well, maybe you should just back up a little bit and explain, because most people won't be familiar with how you measure gravity with the Cavendish balance.
Okay, I have some pictures of my own experiment here. Yeah, that's actually the next slide. So this was in Greece in my family factory. And for air isolation, I put this all into a container. And you have here two water buckets, and on the left and on the right, again, two water buckets. And here a glass ceiling to isolate the air, and a tiny hole in the middle where there's a string going through. And so you have a beam in the middle, so you can see the beam here. And the gravity of the two of the water, those are the source masses. They attract the beam, the sides of the beam, and but the tension of the string is pulling it back. So it's an oscillation. It goes back and forth, back and forth. And by measuring the oscillation angle and the period, you can calculate the gravitational constant.
And this is done with two lots of water, but it could be done with different materials, water on one side and iron on the other, for example.
Normally you have one material for the source mass, so those would be the two buckets, and the test mass would be the material of the small masses at the end of at the two ends of the beam. So those are the two materials I list down there. For example, here Fe and Pt, iron and platinum. So that means that the two buckets had iron in them, let's say, and the small things at the end of the beam were platinum, for example.
But what about the beam itself? Don't you have to count that?
Yes, although that, yeah, you would have to count that. And in the past, I thought that would be very significant, but actually, I saw some calculations that say that it's really the bulk of the effect is from the end of the beam because it's closest to the buckets.
I see.
Mm.
Okay, thanks for explaining. So can we go back to the graph where you've looked at the G as measured by the oscillations of the beam between these two sources?
Yeah.
Is actually different. And did all these people use the same method you've just described?
Well, Hubler here from Germany, he did a type of experiment that I normally don't include in this list because it was a large scale experiment with a whole lake. So it was measuring the gravity of a whole lake. And usually that cannot go well because normally a physics experiment have to be very isolated and they should, I mean, I had to seal it from air and everything, and it's hard to do it with something very big. So most of such experiment get some ridiculous values that are not really to be taken seriously. Yeah, all the others should be, yeah, all the others are basically the same experiment, the Cavendish experiment. I'm looking over to see, yeah, it's all the same, yeah.
So then the variation in G that we see on this graph, right down at the left side where you've got the lowest measurement is this one, what's that?
6.666.
Yes. And what measure, oh, that's lead. So,
Yeah, so Ponticus is the one of the very few who measured different materials, and he published that in 1971. And that's a very interesting case because he measured the different materials and he got different numbers, and he published that in French. But then 1 year later, when he published the English version, he was too embarrassed to list different values for different materials. And so what he did is he put everything in a computer and he did some data homogenization, which they also like to do in climate science sometimes. And so to make all the numbers similar to each other. But others who have done meta-analysis of all the measurements of G point out, I think, who was it? Was it Luther? He pointed out that he pointed out that there's no explanation for why his values suddenly totally changed and became the same.
I see. But there's all these values show quite a big variation from 6.666 right up to the top one, 2005. What's that? Balch. Um,
Yeah, 2005.
6.675. I mean, this is
Mm.
given the fact they're giving three places of decimals and implying an incredible accuracy. I mean, these are way beyond the error. Now, what do most physicists think about these data with different materials? Do they just say they're experimental errors and everything ought to have the same gravity per unit mass? What's the conventional view?
Well, those who have seen my work are usually quite interested and impressed, but it's something that they cannot do much with because everyone is already used to working in a certain way, and then if they want to change, they would have to study my theory, and it could take them a few years. So.
I see, but do you think then that this variation in materials is enough to explain the remarkable variation in measurements of the fundamental constant G that are published in the
Yeah, of course. Yeah, I mean, you see how it fits the blue curve, and you know this before 2014, I was kind of neglecting the test mass composition. I was only looking at the source mass, which is very wrong, and there were reasons why I ignored it, and I didn't realize that it's very important. But after accounting for both, the odds that this is a coincidence went down to 1 in 10 to the power of 13. So the odds you have to reach in order to get a Nobel Prize is 1 in 10 to the power of 6, like 1 in 3 million, and this is much higher statistical significance. Yeah.
So when you look at I mean, the kind of data I alluded to in my book, The Science Delusion, some of them were average data because normally they publish averages, don't they? They measure it in different labs and then average it.
Well, Codata publishes the averages, the individual papers, they show the single values, and Codata publishes the averages. And something very good that Codata did was around the year 2000, they realized what a mess this is. You're not the only one who realized it. They also realized that it's a huge mess. So what they did is they suddenly increased the standard deviations by a factor of 10 or was it 100? I don't know. It was so narrow, and then they made it like this in order to get people into trying to measure it better. And they did. There was a lot of effort to measure it better, but what they did is everyone agreed to only use stainless steel, nothing else. That's how they reached an agreement.
Oh, I see. And then are they getting consistent results now they stick to the same material?
Yes, very consistent. So in the year 2000, Gundlach got very famous for measuring big G with incredible precision, according to himself. And well, for this material, it was very precise. And then Luo from China got, and his team from Wuhan, actually, they got pretty much the same number in 2018, and so many people think, okay, it's settled now. Gundlach's value and Luo's value agree, and it should be this number now.
I see. So all these variations due to different materials that you've drawn attention to here, that's all just swept under the carpet, is it? And ignored?
Yes. the only other attempt to explain it was in 2016 or so. A group of people, they claimed the variation in time of something 6 years or 5.5 years, but they had like 5 measurements there in the graph. And then 1 year later, people just added some more measurements into it, and the pattern disappeared. And here in my graph, I really included every measurement I could find. I was searching for 2 years to find more measurements. I really cannot find more than these, which I already found. And I only excluded one person here, which was a Russian, Karagios. His measurements were of low quality. So I only excluded one person. So I included everyone from the last 55 years.
These measurements were done with the Cavendish thing, the swiveling beam, but you also wrote intriguingly about fascinating experiments I'd never heard of before, where people drop things in an aluminium container down a tower and film them as they fall. And if they have the same gravity as the container, then they'd stay in the right place. But if they're a different gravity, then they'd sort of float up. And some of them floated up. Could you say a little bit about that?
Yeah. First of all, to explain why different materials would fall differently if they have different gravity. Well, in Newton's theory, you have when you calculate things like free fall acceleration, you have mass times acceleration equals the gravitational potential energy, and then because both sides have mass, so it cancels out, the mass cancels out, but in my case I have no mass in the gravity part and nothing can cancel out. That's why they fall differently. So Sass did a free fall experiment in the tower in Bremen, free fall tower, but he could only do one single trial. He was barred from repeating the experiment because they didn't like his conclusions. They said it must have been somehow shaky, and that's why some of the masses floated up. And the whole thing landed in front of the courts. So he had a legal battle about this instead of just repeating the experiment, which only takes a couple of seconds.
So the thing on the left is the picture of the tower, is it? That tunnel-like thing is looking down the tower. And what's that in the middle, that structure in the middle that's held on with string?
Yeah, that should be the aluminium. Yeah, the aluminium capsule. I'm not so sure. Yeah.
And what's the thing at the top? The round thing, on the right-hand side, seems to be above everything. Is that just?
Yeah, I don't know why it's hung down on a string, and so I should have given a bit more thought about this picture. Yeah, but on the right side you see the inside of the capsule, which is dropping, and you can see that lithium is floating up, carbon is floating up, and lead is floating up. Pb is lead, and so aluminium and iron don't float up because iron is falling faster than the capsule because it's made of aluminium, and so it sticks to the ground. And aluminium is falling at the same rate, so it also stays on the ground. Now beryllium and boron, they should have left the ground, but it could be due to adhesion. Especially in a vacuum, there's adhesion.
I see.
And yeah.
So were these all in the same capsule at the same time?
Yes.
And so he dropped the capsule. This is filmed as it falls, and it shows the lithium floating up away from the base of the capsule. I see. So it's not very clear. It looks to me as if there's beryllium. There is somewhere seems to be a black mark. What is that? It's not.
That's just a mark. Well, we could show the video.
Oh, let's see the video. That would be more interesting to see that.
Okay, the video. How do I share the video? Okay, if I just share my browser, yes. So that's his website. He passed away in 2022. And his website is basically talking about how he was ostracized and how he couldn't repeat the experiment. So here's the video. You see they're floating up here. And so I think the fact that carbon lifted off a bit later shows that adhesion can be a factor, and it also shows that it could have not been because of something hit the container, because it was in midair at that moment.
I see. Well, what's this drop tower? I mean, this is like a modern version of Galileo's famous experiment with the Tower of Pisa, isn't it? Where he was claiming that everything falls at the same speed.
Yeah, but Galileo never did the experiment. It was just a thought experiment. He only did experiments with inclined surfaces. Yeah, he never did a free fall experiment.
Anyway, obviously he couldn't have done it with this kind of accuracy, but that's the kind of thing everyone will have heard of, the supposed leaning tower of Pisa experiment. So presumably the non-leaning tower of Bremen in Germany, they've put there for some reason to test something about falling. So
I called them, but they say they would never drop anything without the capsule. They always need their capsule. We wouldn't like to do that, they said.
I see, but even with the capsule, he did it with the capsule, but then it gave results they didn't like. But what are they doing that they do like then? To build a whole tower and to get
Yes.
results with a capsule, you don't like ones that show things move at different speeds. What's the whole point of having the tower if they're not interested in the results?
The point they have is they research weightlessness for companies that want to launch things into space. So basically, they take those few seconds of weightlessness and, I don't know, research how liquids behave under weightlessness. But I mean, they could do that on a space station.
Oh, I see.
I'm not sure what's the purpose.
So it wasn't designed in order to test the kind of thing that you've just been talking about.
No, it's totally, nobody's using free fall experiments except of me. Nobody's using free fall experiments to test the equivalence principle. If you look on Wikipedia, they mention some ancient Greek person 2000 years ago dropping things. And then Galileo, who didn't do it actually. And then there's only one single test of the free fall, of the equivalence principle using free fall. But that was using a height of only 60 centimeters, which is ridiculous. You cannot see anything with that small height. Even me, many rooms I have been in were too small to do a proper test. This one is big enough now, but I had to buy a rod to, we'll restart the experiments again soon. And so that's not the only mistake they did. They also, instead of measuring the free fall time, which is the crucial thing to measure, they only measured the terminal velocity. And if you look at the terminal velocity only, the differences you expect from different materials will be so tiny you cannot possibly measure it. But if you measure the total free fall time, it builds up because it's not a single, it's like the whole, you measure the whole time.
Yes.
And then it's easy to measure. So for example, at a height of about 2 meters, lead and steel will have a difference of 0.0003 seconds, which is easy to measure with this device I can show you. So this is my free fall adapter. Of course, it has many components, but here's a magnet and it's released from here. You push a button and it's released. I recorded many videos of me doing that. I did that for more than almost a year. Yeah.
But presumably you have to have, like they do in Bremen, a container, because otherwise you get different air resistance and so on.
Actually, no, because you can use vending machine balls and you can fill them with equal masses and then in different materials, and then the air resistance will be exactly the same and the mass will be exactly the same.
But that's what I mean. You're using a container, the ball as a container that would have the same air resistance and friction and stuff.
Yeah. Yeah, I'm using vending machine balls, so I can show you. So I have these vending machine balls here, and I just
can't-
fill them with different things.
Oh, yes.
Yeah.
So anyway, this is all to measure what you're showing here, these different values of G for materials of the same apparent mass.
Yeah.
And so you've got more data here. What is all this?
This here actually is free fall experiments, free fall interferometer experiments with, for neutrinos. So they're not doing many. They're not doing normal free fall experiment, but they're doing some with single particles. They're doing some, for example, they did free fall experiment with antimatter to see if it falls up or down, and it falls down. Yeah.
Falls down. But I can't
Yeah.
understand. Since dust particles just sort of float in the air, I can't see how you could possibly do it with a neutrino to see.
In a vacuum, and it's neutral. That's why you cannot do it with an electron or proton, because they're always going all over the place because electromagnetism is so much stronger than gravity.
Exactly, but I'm surprised that you can consider that a neutron or a neutron.
Yeah, neutron. Yeah.
I thought neutrons weren't very stable outside atoms.
Oh, they're very stable for 10.5 minutes. So
you can actually measure, you can get individual neutrons and measure how fast they fall.
yeah, and surprisingly, all the experiments that have been done, all the references you see here, all of them are falling 1% slower than normally, which is exactly what my theory predicts.
You mean normally they're falling 1% slower than they ought to according to their mass?
Well, all objects are supposed to fall at the same rate in a vacuum, right? According to Newton and Einstein, that's the equivalence principle. Everything falls exactly at the same rate, regardless of mass.
So
an elephant and a feather falls at the same rate according to Newton. So and it's not the mass that makes a difference, but the material, according to my theory.
So the point is, the mass of the neutron would lead you to expect it to fall faster or slower than it actually does. Is it faster or slower?
It falls slower than steel, for example. Yeah, 1%, and exactly that 1% is what I expect from the theory, from the fact that it doesn't have any binding energy, so it has very much less gravity.
Okay, so then perhaps then we could come on to your theory about why the binding energy. I mean, everyone agrees there's binding energy from the strong nuclear force holding all these neutrons and protons together inside the nucleus. So binding energy is not controversial.
Yeah.
So I can't see why your theory is so controversial. If everyone agrees binding energy exists, it has a negative value, and that everyone agrees about the value of the protons and neutrons, what they're supposed to weigh. I can't understand why it's so controversial.
Well, it's controversial because it says that I say that gravity depends on the number of particles, and the others say it depends on mass or mass energy. So it's totally different. So for them, that mass gets reduced, it doesn't matter, it doesn't make a difference, because according to them, it depends on the mass simply and nothing else.
Okay, well then, why do you think particles have? I mean, gravity is a mystery anyway. Even if you just think it's mass, it's mysterious, to me at least, why it works. But why do you think the particles have this effect? Why do they have
Well, okay,
gravitation at all? And what
okay.
is it about particles that gives them this ability? And also, do you just ignore electrons because they're obviously part of the atom as well?
Yeah, let's get to that in a moment. So in my theory, and actually in every quantum gravity theory, you have to quantize space. And the way to do it is normally you have to say that there is some kind of a duality between particles in space, that every particle is a quantum of space. And so, but then you would say, okay, here's one particle, here's another. How can they build space? They're so far apart. Well, it's not the real particles, but the virtual particles of the quantum vacuum, which is all encompassing, it's everywhere. And so in my theory, it's spheres that overlap. And so instead of going from A to B, you go on the surface of those spheres. I got a picture of that. I'm screen sharing that now. Where is it? Here. So here you see a straight line, and then you zoom in and you see it's not a two-dimensional space, but actually has less than 2 dimensions. It has like 1.999 or something, because it's going on the surface of those bubbles. And you can imagine that our 3D space is similar and made of these bubbles. So when you use this theory, then imagine you take a particle and you put it into the empty space, which already has all of these many bubbles there. You put one particle there, for example, an electron, and it emits a lot of virtual particles, which corresponds to many more bubbles. And so it has a charge, and therefore it emits virtual photons. And if you have a quark, then it emits virtual gluons. And all of these charges, charges and hypercharges, they increase the local density of space, basically. And so there are more pathways leading through that region of space. So that's what gravity really is. And it's so weak because you already have so many of these bubbles already in empty space that if you add one particle, it doesn't make any difference. You have to add a huge planet in order for it to be noticeable. And that's why you don't need gravitons or anything. You can just say gravity is a side effect of the other forces we know. You don't need 4 forces. You can just do with 3 forces and treat gravity as a side effect. So you get chromogravity, the gravity that comes from the strong force, the nuclear force. That's protons and neutrons, and you get electrogravity, which I guess a lot of people will like, but actually it's not so relevant because it's much weaker and hard to detect. Normally you have chromogravity is what we deal with in everyday life and in physics.
But if you ignore the mass of electrons in your theory, you just treat the number of protons and neutrons as the source of gravity, you ignore electrons, then how do the sums work out? Because the electrons, I mean, they have much less mass, but they've still got mass.
Well, gravity does not depend on mass in my theory. Depends on a number of particles, but I get your point, yeah.
But
yeah,
you ignore the what you call electrogravity because that depends on electrons because that's short range. Is that why you ignore it?
Yeah, exactly. It's 40 meters according to my theory. That's because those virtual particles they have only a limited lifetime and they cannot reach very far. But for the strong force, the gluons are self-interacting, and so one gluon gives birth to another one, and so it can it keeps being strong for the matter of fact is that in my theory, the size of those space quanta, those spheres, depends on the energy of the particle. And so for those virtual particles that go very far away, their energy is very, very low, and then they become smaller than the smallest sensible length. and then you can basically ignore them. Then they are gravitationally ineffective.
So are you saying then that gravity depends on, say, a body like the Earth or any massive body radiating out, as it were, virtual particles as gluons that
Yes.
radiate in all directions?
Mm-hmm.
So it's a kind of
Yes.
and a radiation of virtual particles. But okay, well, what speed do they radiate at, these virtual particles?
Yeah, the speed of light, but well, maybe gluons have a tiny mass, but that's a bit speculative. And it would only reduce their speed by almost a noticeable amount. Yeah.
But when you say they go at the speed of light, is that because in this instance you're simply being conventional, or because there's evidence for it?
Well, the strong force is assumed to go with the speed of light because gluons don't have mass. And I say maybe they have mass, but it's very tiny. And we know from neutrinos that they go with the speed of light, almost the speed of light. And that's something you can measure. You can emit neutrinos in this laboratory, and it can reach the other side of the Earth because they go right through the Earth. And you only measure a tiny amount of them, but you can measure how long it took them to get from A to B. So we know that particles that are very light go at almost the speed of light, and if their mass is 0, then they go at absolute the speed of light.
Well, you see, I get confused by unconventional physics because I'm not a physicist. But I was very impressed by that paper by Van Flandern that argues that gravity travels much faster than the speed of light. Partly because, as he points out, when people are actually doing calculations about gravity, about spaceships and planets and things, they assume it's instantaneous. They don't assume it's going at the speed of light. They actually assume in their calculations it's instantaneous. So he argued for a variety of reasons is vast.
Well, NASA is accounting for that difference. They do account for the speed of light. And NASA does account for that in their calculations.
For gravitational effects.
Yes.
So then what do you think of Van Flandern's article where he says that it's billions of times the speed of light? Do you think he just got it wrong, or what?
Yeah, I'm pretty sure. Yeah. Yeah.
On empirical grounds, or
yeah, I've looked into that. I mean, yeah, I mean it's yeah, we have measured gravitational waves, and the gravitational waves also come at the same time as the visual signals, or almost at the same time. Of course, some people doubt the gravitational wave measurements, which started in 2015, but they've built several 2 or 3 gravitational waves observatories, so that it only counts as a signal if it hits both of them at the same simultaneously. Yeah.
But now, if we can come back to your gluon theory about radiating gluons as the basis of gravity, why is it then gluons are to do with the strong nuclear force, are they? Or are they to do with the... But then why are they... If the strong nuclear force is what holds protons and neutrons together in the nucleus, then why is it proportional to the number of protons and neutrons instead of the amount of strong nuclear force?
Yes, well, it's well, if you look at the strong force, the color charge, you have basically 3 colors. They're not really colors, but 3 neutralize each other. So for electromagnetism, you have plus and minus neutralizing each other, and here you have 3 things neutralizing, and so that's why we call them colors. They're not really colors. So outside the nucleus, it's all white. Basically, the 3 colors blend into whiteness, and so there's no strong force anymore. You don't feel it. But the total number of virtual particles that flow out and cause gravity depends on how many quarks you have, and that's basically the same as how many protons and neutrons you have, because every nucleon has 3 quarks. So you can say it depends on the number of quarks or on the number of baryons, protons or neutrons. It's exactly the same thing.
But to cause gravity, not only do they have to flow out, they have to be received by the object that's gravitating towards them. So when all these gluons flowing out hit an object in space, how do they cause the attraction to occur? Absorbed.
Virtual particles don't really hit something. They're part of empty space. So what they're doing is they increase the density they increase the pixels basically. So you get a higher resolution of space, and there are more pathways going through. And so when particles zigzag their way through this granular space, which is what I call it, then there are more zags than zigs here. Let's say this is zig and this is zag. There are more zags than zigs, and then it gravitates towards that object. So if I throw a pen and it falls down, basically it's because there are more zags than zigs going, more pathways going down than going up. So that's what I use instead of curvature. I don't use curved space.
But virtual particles going through granular space are actually leading to a measurable force. I mean, you and I are both sitting down at the moment. We're not floating around. The gravitational force is a measurable force on our bodies, and it affects everything we experience in daily life. So how do virtual particles produce this force? Just by going...
Well, the other forces, the normal forces, are also produced by virtual particles. They're called gauge bosons also, when we talk about their force effect. But that has to do with the wave function, how through the wave function these forces emerge. But in this case, it's really only about the structure of space and how there are more pathways here than there, and that's gravity.
So, okay, so I'm just trying to get into focus what your theory is saying different from other people and what it's saying the same thing as other people. So what is this now? We've just got to chromogravity.
Okay.
Yeah.
Yeah, so here, this is basically the first slide that deals with chromogravity. So here I calculate the gravity of hydrogen. So I take the G value of iron, which has to be measured. It has to be measured in an experiment. And then I multiply that with this here, which this is the mass of the iron atom. And this is the mass of the iron atom if you just count the number of protons and neutrons. So this is number of protons times the mass of the proton, number of neutrons times mass of the neutron. So this is the mass you would expect naively if there wasn't no binding energy. And so the mass it actually has is smaller than what you would expect because of this negative energy. And so this is a small number, this is a big number. So this gets smaller. So this big G value of iron, you make it smaller. You basically calculate out all the binding energy to know what the gravity should be if you remove all that binding energy. So that's how you get down to hydrogen. And then when you have, and this is the detailed calculation, so the different isotopes, so you have so many percent, so this is 5%, 5.8%, this is 191%, the different isotopes together with their atomic masses. So this is the inertial mass, the normal mass we deal with in everyday life. And this is gravitational mass, which basically just means the mass you would expect if you just naively sum up all the protons and neutrons. So you have here 26 protons in every case, because all the isotopes, the number of protons is always the same, but the number of neutrons is different. So here you have 28 neutrons, here you have 30, then 31, and so on. So, and then you take this and divide it by this number, divide by this number. So here you see the difference in the mass. So this is the mass you would expect. 56 is the mass of iron that you would expect, but actually because of the negative energy, it's smaller. It's this number. So you get a G value of hydrogen of 6.6135, which is very, very low. Nobody has seen such a low G value. And then when you calculate the G value of any other element, you do the opposite. You start from hydrogen and you multiply the other, you divide the other way around. You divide this, the lower one, with the upper one, and then you can get the G-value of any element. Here the four different isotopes of lead, and here you have the different number of protons and neutrons, and these are the atomic masses of the proton and the neutron. And here the percentages, so how many percent in nature, how many percent is there. So there's 52% this and 22% this and so on. So you get a G-value of lead of 6.667878. I omitted the plus minus, would be plus minus 0.0007. Yeah, depends on, or 0.0022, something like that.
Iron, from your point of view, iron is an anomalously high gravitation. But you say they've recently standardized all the measurements using steel balls, which are all steel, which presumably...
Yeah, so they treat Earth like a steel ball. They treat Earth like a steel ball, and that's why in astrophysics everything goes wrong. The perihelion precession that Einstein was so proud of is wrong since 2017. The Taylor pulsar, which was hailed the biggest success of general relativity, is wrong since 2010. Nobody knows about it, almost nobody. Yeah, and if you account for all these material differences, then everything falls into place. But I should mention that later because we're at the first few slides here.
All right, so we've got to the difference between the gravity depends on the number of protons and neutrons. It's all to do with the strong nuclear force and the radiating out, as it were, of gluons, virtual particles. So where do we go next on your theory?
Well, just some small details, not some examples here. So for molecules, one has to be careful. You have to two times the inertial mass of hydrogen and then oxygen. So you have two hydrogen atoms and one oxygen, and so you have to do this carefully and not like take an average of the two or something, which is what I did at the beginning. But this is the careful way to do it and the correct one. So for water, it's 6.661. And then for mixed materials, you have to, sorry, this picture is a mess, but for mixed materials, you have to be careful to translate the weight percentages into atomic percentages to know how many atoms there are of each material.
Yes. Okay.
And here it's important to take the geometric mean of the two materials. So you have the G-value of water, let's say, and the G-value of hydrogen. So what's the resulting G-value when the test mass and the source mass have different materials? The answer is you have to multiply the two G-values and then take the square root of that. That's called the geometric mean.
All right. So we've got the number of particles. We've got this gluons, virtual gluons going through granular space. Is granular space your own idea, or is that a standard view because of the Planck length?
Well, usual approach to quantum gravity is to quantize everything in a way that you have kind of like space atoms, like in loop quantum gravity, but they're like very simple pixels, all of the same size. But my picture is totally different because I have different frequencies or different sizes. So my elementary spaces actually started out as black holes. So I thought maybe because electrons are said to be infinitely small, so they would have to be like a black hole. But then I changed the constant of proportionality, and so they are much bigger than they would be. Normally, they would be much smaller than the Planck length. But because they are not black holes, but just elementary spaces, space atoms, they are quite big. Like an electron has the size, a resting electron has the size of 10 to the power of minus 21 meters. which is pretty big compared with string theory, which deals with things that will be forever unmeasurable. And at certain energies, we can certainly reach the size of the elementary space, of the space quantum, becomes bigger than the wavelength, and that's when you have a chance to actually observe these elementary spaces. And so I think that's the explanation for why we cannot observe any new particles. The new particle accelerator at CERN, which is not so new anymore, it didn't find anything new except of the Higgs boson, and that's because there really is a particle desert after the Higgs boson. There is nothing new to come, because when you use higher energies, you think you're probing smaller scales, but you're not, because your particles become bigger and you cannot use them to probe smaller things. It's like you're having a big finger and you're trying to find some small things. It's impossible.
I see. So then, where do you go next with your theory? I mean, we've got those different sized particles, we've got the gluons. Does it work? What's the next step, if there is a next step? Or is that it?
Well, my book is already too thick to carry around anywhere. It's like 800 pages, and it's DNA4. If I use a normal format, it would already be 1,600 pages or something. So it's already too much.
Well, I know it's enormous. It's vast. It covers a huge range of physics. I've read various chapters in it.
Yeah,
certainly haven't read all 700. But gravity is just part of your theory, is it? I mean,
yeah.
How does gravity tie in with the larger theory then?
Yeah, well, in cosmology, for example, I agree with something Newton said. Newton was asked, if there's universal gravity and everything has gravity, then why isn't everything collapsing? Why isn't the whole universe collapsing? And his answer was very good. He said, if the universe is infinite and has no center, then there's no center of mass, and then it cannot collapse. And I agree with that, but Einstein doesn't agree with that. They somehow imagine that even without a center of gravity, you can still have gravity, which doesn't make much sense to me. And it relies on the Copernican principle to be right, and it's certainly not correct.
Just to remind you what the Copernican principle is.
That everything is the same in all directions, and it's totally not true. Earth is actually kind of in a special place because of quantum mechanics, because we are observing it, and quantum mechanics actually leads to a kind of solipsism, but not of one person, but just of the whole globe, basically. But that's very controversial, and the alien people don't like it. Yeah.
I see. Okay, well, we're obviously getting into deep water here, but what are the implications of your hypothesis then for so-called dark matter and dark energy? Do you think they actually?
Yeah, well, let me put the slides into that position. So, okay, so entropic expansion cosmology is basically saying that the universe expands in order to compensate the entropy increase in black holes. So that can only work if gravity is out of the picture. If Newton was right in saying that you don't have gravity, there's no center of mass. Only then can there be something, such a magical, you could say, principle, which is non-local. So this is actually an example of a new non-local principle in physics. I mean, we have in parapsychology, we have telepathy and remote viewing, and then in physics, yeah, we have quantum entanglement. But here we have something different. We have such a principle in cosmology. The whole universe basically conspiring to make sure the entropy density doesn't change. So whenever a black hole is growing, space is expanding to compensate for that entropy increase. So if you have a box, transparent box through which everything can go, the entropy inside that box is always the same. So that's an open system. In closed system, entropy is increasing in a closed system, but the universe is not a closed system. You cannot even talk about the the entropy of the universe because it's infinite. So you have to talk about entropy density.
So you're giving a different reason for the expansion of the universe from the usual one then?
Yes, and I say that actually it started not with a big bang, but with a big tardiness, so big slowness. Everything was extremely slow and expanding at a very slow rate, and then it accelerated. And the reason for the acceleration is if you feed a black hole matter in linear way, you give it one donut at a time, let's say, then because the entropy depends on the surface area of black hole, and that involves a square. So for the surface area, for an area, you have a square. So that's why it's like a quadratic function. And so if it was very slow at the beginning, then it took a long time for it to reach the density it has now, which is a very low density. And that's why the age of the universe is much, much larger. And it's actually 42 trillion years. And that number, it's funny because that number coincides with the number given in that movie Hitchhiker's Guide to the Galaxy, where that supercomputer says the answer to everything, the meaning of life is 42. And I'm saying the same number, but it's just a coincidence. Yeah.
I see. And so yours is 42 trillion years because the usual...
Plus minus one.
Oh, I see. Well, I mean, there's not much scope for observation and to know about observational error, I suppose. But this is a calculation.
Yeah.
But the normal theory is that the universe starts with rapid inflation and then it slows down, but it's still expanding. So,
well, the inflation was stacked on top of the Big Bang theory. It doesn't really belong to it. It was used to explain why the universe is so totally flat. And the chance for it being so totally flat in Einstein's theory is 1 in 10 to the power of 62. It's like totally impossible. So on grounds of that, Einstein's cosmology should have been disregarded already in an instance.
So the inflation was added to try and fix this problem.
Flatness problem, yeah.
But you still have a Big Bang, except your universe expands very, very slowly for a long time and speeds up later rather than expanding very fast.
I wouldn't call it a Big Bang because the densities that are reached are only 6,000 Kelvin. Even the sun is hotter at the center. So by all means, it's not a Big Bang theory. It's like totally the opposite. Everything is cool. Everything is boring, kind of, at the beginning.
But it's also small at the beginning, is it? A lot small, very small.
No, actually, changing size is only a feature of theories where the universe is a closed universe, which is a collapsing universe. But even in the mainstream, which is using Einstein's cosmology or Friedmann's cosmology, the universe is already not collapsing. We see that it's expanding faster and faster. And so they don't have the option to have a finite universe. In the mainstream and in my theory, the universe is infinite. And so it just starts with a high density and the density gets lower and lower.
I see. And why does that happen?
Yeah, so in the mainstream, the reason why it's very fast, the expansion is very fast at the beginning, is because in the mainstream you have gravity even without a center of gravity. And so they need to make sure the universe doesn't collapse back in. So that's why it needs to be very fast at the beginning, actually 17 times faster than now. And then it slowed down and then accelerated again because of this magical thing called dark energy, which certainly does not exist, and it's not a real theory because it's freely adjustable parameter. There's a lot of evidence, like the pendulum experiments here, done by somebody I totally don't know, and they confirmed my theory very, 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 very well. And he did one in 2023 and then another one in 2024. And in the first run, all the elements lined up in a perfect hierarchy. And the chance of that is 1 in 24. And then he repeated it again and was, again, a very good agreement. And he will do another series of experiments this year. And I guess I will receive it in a few months. And he didn't know anything about it. They didn't know what to expect. When he saw the result, he thought, oh, that's a tiny result. And he's not he's just an experimenter. He doesn't know much physics. So he thought, oh, that's a tiny difference. It's not relevant, but I told him it's exactly the difference that is expected.
So let's just to get it clear in my mind, he's got a pendulum, and it's the pendulum bob that's made of different materials, is it? Is that what
Yes, yes.
this is all about?
And he even used a vacuum. Yeah, it's in a vacuum. Yeah.
I see. And so the rate at which the pendulum of a given length swings depends on the mass of the bob, does it? The pendulum, the weight.
Now, in a vacuum, it should be similar to free fall, so they should all oscillate in the same way.
I see. And the point
Similar
is,
to free fall. Yeah.
the point is they don't oscillate in the same way, and
Yeah, there's small
it
differences.
depends on the material you use, and the discrepancies from them all being the same. The discrepancies fit your theory about the nature of the material.
Yeah, the agreement is 99.99%, 99.97%, and so on. And it's totally unbiased because he didn't have any idea what to expect. He had not contacted me when he did the first run of the experiment. He was inspired by that free fall tower experiment, actually. And he only got to know me a month after he did the experiment.
And is he still doing this kind of research?
Yeah, he's going to publish the next one this year, the third one. Yeah, he's an American who lives in Italy, but he's very secretive. I don't know much about him. Yeah, and I only communicate with him through email. And here, the next slide, I did some experiments weighing things with a balance, and then weighing the mass with a balance, and then weighing the gravity with a scale. So if it's a real scale and it's like a feather, like a spring scale, then it should be affected by gravity and measure actual gravity. So I did some measurements with that, with many different materials, but it's not so reliable because the measurement precision is very, very low with this. Because if you buy an expensive scale, it's not a scale anymore, it's a balance, and then you cannot measure gravity with it. So I need a gravimeter, but they cost like 100,000 US dollars. So if you buy a modern one, I would have to buy some archaic one.
What is a gravimeter?
There are two types. There are free-fall gravimeters, which are absolute gravimeters. They have some small free-falling mass inside in a vacuum. But the more precise ones actually are the relative gravimeters, and they're spring gravimeters, and they're basically a spring with a mass attached. And so if you have more gravity, it's going down more. But normally you cannot open it and take out the mass and try another one. So you can only use it to measure the gravity in your mountainous area, for example, or at the beach to see the differences in gravity. I would like to open it and actually measure the weight in Newton of the test mass, but it's very difficult. I asked one company in Canada, but they were unwilling to do that, and the devices are too expensive, those that I've seen.
I see.
And this slide is about gravity manipulation. So basically, you could make some science fiction stuff reality with this, but it was very difficult. So if you could inflate mass, which you can do in a particle accelerator, you're accelerating particles and they get heavier and heavier. Then you increase the mass, but you don't increase the number of particles. And then you have very little number of particles per kilogram mass. And that means you have very little gravity and the things would fall slower. But it would be very hard because the accelerated particles would have to be heavier than the container. And that's very, very difficult technically to do that.
Mm.
So that would be, and when you use it in Earth orbit, you would get artificial gravity because the people would fall faster than the spaceship. They would have a different orbit and they would be pressed against the floor. Yeah, and And I said that the highest gravity is the gravity of iron, but actually that's not quite true, because if you look at neutron stars or black holes, they have negative, a lot of negative mass. As I said, Earth has a lot of negative mass, some little, not much. But for neutron stars, it's like 15 to 20%. And so that means the mass is reduced like in iron, and the number of particles is not. And so you have very high G values for neutron stars. So for a neutron star, it's 8 instead of, you're used to 6.67, and this here is 8. And for black holes, it's 9. So that means the masses of the neutron stars and black holes, they're different from what we think. And if you account for that, then the gap between the masses of neutron stars and black holes closes magically. So there's a big problem in astrophysics. If you make a statistics of all the neutron stars and all the black holes, you get the neutron stars here and the black holes here, but there's a huge gap in between, and there should be no gap, because if a star is so heavy that it cannot become a neutron star anymore, it becomes a black hole. So there should be no gap. And if you use my masses of the stars, the neutron stars and black holes, then there's no gap anymore. The gap closes, it solves this problem. I solved this in 2022.
I see. So
yeah. Mm-hmm. Yeah, and it also gets, so the heaviest, the lightest black hole is 3.3 sun masses, and the heaviest neutron star is 2.35. So that's a huge gap, 3.3 and 2.3, huge gap. But if you look at the SPD masses, like the masses according to my theory, then the gap is closed. Then the gap is only 0.3 sun masses, so it's closed. The gap is closed then. Yeah.
okay, I don't understand why closing the gap's significant or important.
Well, it's important because statistically it's impossible to have found hundreds of black holes and neutron stars, and they all have, like, let's say 3.5 sun masses, 3.6, 3.7, and statistically you should find the lightest black hole should be right above the heaviest neutron star. There should be no gap. So if you just know a few stars, then it's fine to have a gap. But if you already have hundreds of them and there's still a big gap, then you have to explain the gap.
Oh, I see. Have you got more slides on the theme of gravity then?
More sites?
Well, I mean, is there any other point you'd like to make now before we?
Yeah, some other points. Yeah, it's also closer to the theoretical limit of the biggest mass of a neutron star. Oppenheimer calculated that. He said it's 2.75 sun masses. If you translated it into my theory, it's 2. And what we observed is 1.96. So it's a very close agreement between my theory and what we observed here. So also the theory agrees. And in the mainstream, there's just utter confusion. Nothing seems to fit. And then last year was the most successful year in terms of astrophysics. Because many people say in order to get really well known, I should repeat the successes of Einstein, because Einstein is always hailed for his success with the Mercury perihelion precession and the bending of the light at the sun. And so I did the calculation for the perihelion precession. You have to account for the influence of every single planet. And so when we add them all together, we get here, we see for the different measurements here, Newcomb, 1895. So Einstein agrees here, and my theory also agrees within margins of error. But here for Clemens, 1947, Einstein disagrees, and my theory agrees. So here I wrote 99.98%, which is only the agreement in value. But since it agrees within margins of error, actually it's like 100% agreement. It agrees within margins of error. So the value is not supposed to be 100%.
Mm.
Yeah, and then I also did that for Saturn. And you may ask, why did I do it for every planet? And that's what I was planning to do. My paper, the original title was Periodic Precession of All Planets, but I couldn't do it because it's actually impossible. NASA doesn't give the data. So if you open some standard textbook on this here, and you look for the periodic precession of the planets, it only lists standard deviations for Mercury, plus minus 0.1 arc seconds. And there's a disclaimer at the bottom of the page saying, the values quoted for the observed precessions of the planets are not independent, since in a data analysis, a single parameter is used to characterize all these precessions. So they're not really testing the theory of Einstein there. They're just assuming it. They're testing it on Mercury only, and then they assume, okay, obviously all the planets should be the same. If there's a deviation, it should affect all the planets the same, but they haven't accounted for theories like mine, where different planets have different gravitational constants due to different chemical compositions. But in the case of Saturn, we have independent data, kind of because of the Cassini probe to Saturn. It was there for 13 years. And so the thing is, for the inner planets, they kind of just take the values from theory. For example, the radii of the planets, they just take the orbit period and get the get the distance from that. But for the outer planets, they cannot see how long a year takes so precisely. So they're more inclined to measure things more directly. So that's also the case for the periodic precession. There we have potentially an independent measurement, but really only for Mercury and Saturn. And all the other planets, I need to ask NASA to give me the raw data.
I see. Very good. Well,
yeah. Yeah, this is a bit too much and too complicated, but basically this is about the orbit decay of the double pulsars. They're emitting gravitational waves and they're getting closer to each other. But in my theory, you get a slightly different value because the masses are different. And so the standard theory already doesn't agree within margins of error because they have been observed for 30 years now. No, for 40 years, actually, I think. Yeah, 40 years. And that's why you get to a level of precision where you can already distinguish my theory from Einstein's theory. And that's the case since 2010. We're near, so this is almost the end. This is the experiment from 1922, very archaic experiment, very old, but very precise one, which Einstein used as evidence for his equivalence principle. So this guy measured differences in gravity of different materials, but it was not a Cavendish experiment, but the different materials were on the same beam, and was it's basically measuring the centrifugal force that Earth impedes on such a beam, and so it's already kind of rotating, but it rotates. So they measured if there's a difference coming from different chemical compositions and so forth. So this is quite a complicated experiment. But anyway, the fact that they were on the same beam and okay, one side was suspended a little bit, causing a little bit different gravitational potential. But that's why the effect is extremely tiny. It's so tiny that the experimenter thought, okay, we're gonna ignore all these differences and just pretend it's the same. It's just measurement error. But it cannot be a measurement error because the standard deviations given for each material were actually quite small. The plus minus he gave were very, very small. And Fischbach, Ephraim Fischbach, who is still alive today, he discovered in 1986, he discovered that these differences that Edwards found exactly line up with the binding energy. So he found basically what my theory also predicts, but because the effect was so tiny, he had to assume it's from some fifth force. And so it's not challenging really any of Einstein's theories, just adding some additional force to it, and he made it short range. but my research really shows it's not a fifth force, and gravity is not even a force, it's a side effect. So I'm reducing the number of forces, not like Fischbach, who added a fifth force. He got famous with this fifth force, and it's even mentioned in the textbooks. In the latest version, it's not mentioned anymore, but in this thing, in this version, it's still mentioned. And the last slide is basically the Kepler ratios, and this is quite surprising. Tycho Brahe, who thought that the sun, that the Earth is at the center of the solar system, he made very precise measurements, and in order to interpret them, you just have to switch the position of Earth and the sun, and you get pretty precise values for his time. And he didn't have any theoretical bias. There was no Newton's theory of gravity didn't exist yet, and so he measured for his whole lifetime very precisely, very meticulously, and he found these. Well, he didn't write down these values. It was his student Kepler, who is alleged to may have poisoned him because Tycho Brahe wouldn't show him his data. And anyway, his mentor died, and he looked at the data, and he found that you can see it there on my whiteboard. The ratio between the cube of the orbit radius divided by the square of the time is always a constant. So it's the same for all the planets. But when you actually look at the small differences, so he would just ignore the small differences, but if you look at the differences, you see that they line up with predictions. Not so perfectly because they're quite crude measurements, but you can see that my theory predicts that the value of big G drops the further you go out in the solar system. Mercury, Venus, Earth, so the value of big G goes slightly down. And then after Jupiter, it has a big drop because those are gas giants and they are close to the G value of water and hydrogen, so they are very, very low. And you can see that there's this perfect pattern. Now you could say maybe it's just some measurement error because you go further away from the sun. But then if it was measurement error, then shouldn't it be away from the Earth? Shouldn't be centered around the Earth and not around the sun. But you can see that it follows as I predict. It goes as you go out, it goes slightly down. And when you include modern data, which I did, and at the down two graphs, you have it mixed with modern data. You have for the first 5 planets, you have the original data that Kepler used, and then the modern data. I cannot use the modern data for the inner planets because for the inner planets, they just derive them from the orbit period, and so they're not observing them. Yes, they do the observation with telemetry, but then they just either mix them. Okay, some of them mix them altogether, but NASA actually uses theory for the inner planets and observation for the outer planets, and so I can only make use of the outer planets. This is the last slide.
Well, thank you. I mean, I'm very impressed by your this composition dependence approach to gravity that you've got. And I find it hard to see why you have such a tough time getting this idea across, because it seems to fit the evidence, and unless there are strong counter-arguments you haven't mentioned, it seems that you're just simply confronting inertia, habit, and laziness in your opponents.
Well, I don't find it surprising, and I don't have many opponents. It's just that I operate outside the system. So how can I make these ideas known? It's not so easy. You can do it with the internet. Speaking to you is basically my best chance, you could say. I also spoke with Manas Kafatus, but yeah, didn't have so much of an impact. Video got some views, but he doesn't have a big internet presence like you. He gets invited into big panels, But if it's outside a panel, he doesn't have his own YouTube channel. You have your own YouTube channel. And so you would be more influential here.
Well, I mean, I'm not a physicist, and I don't know how many physicists look at my channel, but um, if
Well, Kurt interviewed you.
if just talking to you can help you, I'm delighted. But you know, I very much hope that your work can receive the proper attention it deserves, and presumably you can publish papers, or at least you do publish papers online. And
Yeah, and mostly upload them onto ResearchGate and academia.edu. And I have wrongly put too much focus on academia.edu, but I realized that it's not very effective. Like there I get like 3 reads a week, and on ResearchGate I get like 100 a week. So when I realized that, I switched over to focus completely on ResearchGate, and since I focus on that, my interest score is going up quite rapidly.
so, if anyone wants to learn more about your work as a result of watching this video, what should they do?
They can go to, they can find my book, The Complete Guide to Quantum Gravity, on Amazon, and they should make sure to not buy the wrong book, because I have republished this book 2 times with some other titles. The first title was Quantum Gravity and the Role of Consciousness in Physics, because when the book was small, there was more focus on consciousness, and since it has become such a complete theory, I thought I should call it The Complete Guide to Quantum Gravity, similar to the title of Roger Penrose's book, like The Road to Reality. Is also kind of, it's a very thick book and trying to tell you everything about reality, but there is kind of left as a mystery. It says that's how what we know, and but the solution is not really provided. Roger Penrose is my main inspiration, actually. I haven't spoken to him yet, but yeah, he has inspired most of the things. The space particle duality was inspired by reading about his twistor theory from 1967, which is also quantizing space and using complex numbers also, yeah.
Mm. And then if anyone wants to look up your papers, then they'd find those on ResearchGate.
Yeah, just my name on ResearchGate, and I make sometimes I make 10 posts a day on Facebook. I'm not so much on other platforms. I'm not on LinkedIn. They have so many scams running on LinkedIn that they are now so strict that you can get banned very easily. They thought because I use the same photo in different accounts, they said, "Oh, you're an imposter or something." But that is me. So I lost my LinkedIn account.
Good. Well, thank you very much. I've really enjoyed encountering your work, reading your papers, and learning about these ingenious experiments. I love the fact that some of these key experiments are so simple, and that normally most people approach or don't approach physics at all because there's a kind of fog of equations that puts off almost everyone except professionals.
Yeah, string theory. I mean, there's no reason why physics should be so complicated. And I mean, even with my theory, even gravity becomes much simpler because, okay, you have to account for the material, but it's not like Einstein's theory where you have these field equations with 16 different tensors, which reduce to 10, and which most physicists, even professors, have solved only a couple of times in their life. And because there you have energy causing gravity, and gravity itself has energy, and that causes again gravity, and again energy, and again gravity. And so you cannot calculate anything precisely in Einstein's theory. It's because of this self-interaction, it's a lot of infinities come up, and that doesn't happen in my theory. And that's the main problem they have in quantum gravity, all the infinities, which you don't have this problem in my theory.
Well, I wish you well with it, and thank you very much.
Thank you,
Bye.
Sheldrake. Yeah.